Not working? We gotta get Ashok. Does this work? Yeah. Ashok, how does this one work?
Here, little button. Press this.
Oh, that's one. Okay, great. Yeah. Which are, I guess, this and this, huh? Yes, and this. Okay, great. Okay, let me begin by thanking the organizers for giving me this opportunity to speak here and for this exciting conference. The title of my talk is Non-Supersymmetric Attractors. I'll begin with some motivation and introduction, tell you about some general ideas, what is an attractor and when it can exist, do an example of type 2A string theory on a Calabi-Yau threefold to illustrate some of these general ideas. All of this will be mainly about spherically symmetric attractors. Then we'll go to rotating black holes and discuss attractors using the entropy function formalism there. I'll end with some comments about connections between the attractor phenomenon and microscopic state counting and some conclusions. I'll draw on the following papers for this talk. These works have been done in collaboration with Kevin Goldstein, Nori Izuka, Rudra Jaina, Dimitri Estefanasi, Suresh Nampuri, Atish Dabolkar, Gautam Mandal, and Ashok Sen in various permutations and combinations. Now there's already a big body of literature even for non-supersymmetric attractors and related topics. I can't do justice to all of that here, but let me summarize at least a few references. The paper of Ferrara, Gibbons, and Kalosh in '97 already discussed some aspects of non-supersymmetric attractors. Papers by Denef, the work of Ashok Sen developing the entropy function formalism, more recent papers of Kalosh and collaborators, Ferrara and collaborators, Krauss and Larson's work which ties in with the discussion on state counting, the paper by Oguri, Waffa and Verlinde, and more recent papers of Waffa and collaborators are some of these references. Okay, let's start with motivation. We all know that string theory has made spectacular progress in understanding the entropy of supersymmetric black holes. It would be great if we can carry this progress further and understand the entropy of non-supersymmetric ones as well. Extremal supersymmetric black holes, I think, are particularly promising in this context. An extremal black hole carries various electric and magnetic charges and has the minimum mass which is allowed given these charges. Now all supersymmetric black holes are extremal, but as you will see today, the class is broader and includes many non-extremal ones as well. Since these includes many non-supersymmetric ones as well. Since these non-supersymmetric extremal black holes share some properties in common with the supersymmetric ones, one might hope that we can make progress in understanding their entropy. And in fact, in today's talk, you'll see that the attractor mechanism which supersymmetric black holes are known to possess is also a property that extremal non-supersymmetric black holes have. Another motivation which is more sort of not as precise at the moment comes from flux compactifications. There are parallels, at least in the mathematics, in how moduli get fixed by fluxes in flux compactifications and how they get fixed at the horizon of a black hole due to the attractor phenomenon. So one might hope that if we can understand these black holes well and in considerable detail, that might shed some light on the difficult questions that now face us in flux compactifications, for example, having to do with the large number of vacua and having to choose between them. Okay, let's start now in general terms in 4 dimensions in a theory which has gravity, gauge fields, and some moduli. Most of this talk will deal with just the 2-derivative theory. And here is the action then. There's the Einstein-Hilbert term, kinetic energy terms for moduli, and terms involving the gauge fields. You see that there's no potential term for the moduli. That is why they are moduli, and they can take varying values at infinity away from any black hole. These moduli are coupled to the gauge fields because they determine the gauge coupling constants FAB and the axionic couplings F tilde AB. Now the attractor mechanism refers to the fact that extremal black holes in such a system have a universal near horizon region determined only by the charges they carry and independent of the asymptotic values that these moduli take. So in more detail, what I mean is the moduli themselves take fixed values at the horizon independent of their asymptotic values and determined by the charges carried by the black hole, and the resulting near horizon geometry also of this black hole is then independent of the asymptotic values and fixed by the charges. In the spherically symmetric case, it has the form AdS2 cross S2. So here's a picture for you. Phi, which I'm plotting along the y-axis, is a modulus. You see it can take varying values at infinity, but regardless of where we start, the radial evolution adjusts itself so that at the horizon, which is this point here, the modulus acquires a universal value just determined by the charges carried by the black hole. Now, as I said, so far this has been explored in the supersymmetric case where it's known to be true, and here we'll ask about non-supersymmetric extremal black holes. And I'll describe for you rotating spherically symmetric black holes and then rotating black holes, but let me just give you what is one of the main conclusions of the talk here, which is we'll find that extremal black holes quite generically exhibit the attractor phenomenon. We can be in 4 dimensions or higher dimensions. We can have a spherically symmetric black hole or a rotating black hole. One can even have a situation where the horizon topology is not spherical, as happens, for example, in a black ring. In all these situations, as long as we are dealing with a black hole or black ring, quite generically there is attractor behavior. Some conditions must be met, and we'll discuss them as we go along, but once they are, this attractor behavior is quite generic. Okay, let's talk about the spherically symmetric case in some more detail now. Of course, spherical symmetry gives rise to a vast simplification. Now things can only vary with one coordinate, the radial coordinate. That makes life much simpler. Here is the Lagrangian I showed you before again in 4 dimensions. If there's spherical symmetry, we can choose coordinates where the metric takes this form. B is the radius of the 2-sphere, and we can solve for the gauge fields, and they take this form. QE and QM are the electric and magnetic charges carried by the black hole, and F with upper index AB is the inverse of the gauge coupling. And after that, we can then write down a one-dimensional action from which we can derive equations of motion that determine the metric and the moduli fields. This has to be supplemented with a quote-unquote energy constraint and extra constraint, which I haven't written down here. Now, particularly important is the third term here in this action, and this term encodes the effects of the gauge fields, and it's essentially proportional to the electromagnetic energy density in the gauge fields. And this term is proportional to what I'm calling V effective, the effective potential, which depends on the electric and magnetic charges of the black hole, and it depends on the moduli. That dependence arises because the gauge couplings and the axionic couplings depend on the moduli. The conditions for the existence of an attractor can be summarized in terms of this effective potential. And basically one finds that there is an attractor phenomena if the effective potential meets 2 conditions. First of all, that it should have a critical point as a function of the moduli, and secondly, this critical point should be a minimum, which is to say the Hessian or the mass matrix computed at the critical point should have positive eigenvalues. The second condition arises if we want the attractor to be stable, and I'll explain to you in a minute what I mean by that. Once these conditions are met, there is, as I said, attractor behavior. The attractor values for the moduli are the critical values. The attractor geometry has the form AdS2 cross S2. The radii of the 2 spaces are equal, and their square is equal to the value of the effective potential at the critical point, which in turn means that the entropy is also proportional to the effective potential at the critical point. Okay, now there's one small caveat which will be important for the example. In situations where there is a 0 eigenvalue of the Hessian, the more general condition is that the critical point must be a minimum. So if we expand the effective potential to beyond quadratic order along these 0 eigenvector directions, the first correction must still leave the effective potential right side up. If the correction, for example, occurs at quartic order, the coupling constant should be positive, lambda. Now flat directions can be present where there are no corrections as we go to higher orders, that's fine, but you can't have a saddle point if we want a stable attractor. So let me give you a flavor for how some of these conclusions are arrived at. The essential complication, of course, here in the non-supersymmetric case is that we have to deal with second order equations of motion, which are difficult to solve, but luckily for us, the analysis of whether there is an attractor and when it is stable is one which can be reduced to perturbation theory, and that is why it can be answered. Let's see how that happens. Let's suppose that the effective potential for the given set of charges meets the first of our conditions and has a critical point. Then let's start by considering the situation where the moduli take values at infinity equal to these critical values, equal to their critical values. It is then consistent to set the moduli to be a constant for all radial location. That's simply because the radial evolution is sourced, if you like, by a gradient term of the effective potential, which vanishes at the critical point. So we can take the moduli to just be a constant. The system then simplifies greatly. It just consists of gravity and some gauge fields, and its extremal black holes are very well known. They are just extremal Reisner-Nordstrom black holes. These have indeed a near horizon geometry of the form I said earlier, AdS2 cross S2, and their radii have the right value in terms of the effective potential at the critical point. So that's our starting point, a zeroth order solution, if you like, and now with that solution in hand, we can take the asymptotic values of the moduli to be a little different from the critical values, so that phi infinity minus phi naught, the critical value is small, and then in order by order in this small parameter, study the resulting solutions. The equations are of course still second order, but now they linearize and so are easy to analyze. So here's what happens to first order. The scalar fields now evolve radially. There are two solutions to the second order equations characterized by the two exponents gamma plus and minus. And we see that if m squared, the second derivative at the critical point, is positive, gamma plus is greater than 0. And that means as r goes to RH is the location of the horizon, this solution corresponding to gamma plus is well behaved. And moreover, and this is the important point, the well-behaved solution vanishes as you go to the horizon. And so that means as you go to the horizon, the first order perturbation dies away, and the solution approaches the zeroth order one we started with, where the moduli were at their critical point. If, of course, m squared was less than 0, then both solutions, it turns out, diverge as you go towards the horizon, and so you don't get attractor behavior, and that is why you need this extra condition of the mass matrix or Hessian being positive for stable attractor behavior. Now you can go to higher orders, and in fact you can formulate an ansatz which works to all orders in perturbation theory, and one finds no new conditions are necessary for attractor behavior. Once the two conditions I told you about are met, to all orders, the perturbations have a good solution, one good solution both for metric and moduli, and these have the property that these perturbations die away as you go to the horizon, so the solution becomes that of the extremal Reisner-Nordstrom black hole we started with the moduli at their critical point. And this then shows that in the system we have attractor behavior, at least in perturbation theory. So what we've shown is that at least in this figure, starting with this value here is the zeroth order solution, because then the modulus is just fixed. What we've shown is for small excursions we still get attractor behavior. Of course, what happens if the excursions become larger is a more difficult question, but just to establish that a particular critical point has a finite basin of attraction, we can do that in perturbation theory, and so this is good enough. Now there's one comment I want to make before I go on. One can think of, roughly speaking, this attractor behavior as a system settling down to its critical point in the deep infrared. If we take a spatial hypersurface in one of these extremal geometries, it has a throat-like form. The horizon lies deep inside the throat, and in the extremal geometry, the horizon is actually an infinite proper distance away. And that in some sense is very important in allowing the system to settle down, the metric and moduli to settle down to universal values. They have an infinite amount of time to run, and so they can forget the memory of where they started out at infinity, where the moduli started out at infinity. If you have a non-extremal black hole, the horizon pops out at some finite proper distance, and then one does not get attractor behavior. The resulting horizon values for the moduli and geometry cares about the asymptotic values of the moduli. Okay, let me discuss an example of type 2A string theory on a Calabi-Yau manifold. The resulting compactification has n equals 2 supersymmetry. There are vector multiplets and hypermultiplets, and it's the vector multiplets which couple then to the gauge fields and which are fixed by the attractor mechanism. one can write down the effective potential very explicitly. The vector multiplet moduli space has a pre-potential, and that determines the Kähler potential. There is a superpotential which depends on the charges carried by the black hole and the pre-potential, and together the superpotential and Kähler potential then give rise to the effective potential. In this case, the black hole can carry 0 brane, 2 brane, 4 brane, and 6 brane charge, and once we know the effective potential, we can ask when there is an attractor and when it is supersymmetric and when it is non-supersymmetric. And I'll not do the most general analysis, but just do a simple case to give you a flavor of how that goes. The basic point I want to illustrate here is that in the non-supersymmetric case, actually you get a rather rich and complicated structure of attractor flows, richer than in the supersymmetric one, in a sense, which you'll see. So let's consider a black hole which carries 0 and 4 brane charge. Then it turns out if this quantity Q0 over d is positive, so that the square root in this first expression is positive, there are supersymmetric solutions, and if it's negative, then you have non-supersymmetric solutions. D is made out of the triple intersection numbers in the 4 brane charges, and the entropy in both cases can be expressed like this, as absolute value of dQ0 with the square root, and this entropy refers to the entropy of the supersymmetric or non-supersymmetric black hole, as the case may be. Okay, so for some range of charges, then you have a black hole which is a non-supersymmetric attractor. At least what this is established is that there is a non-supersymmetric critical point of that effective potential. Now in the supersymmetric case, there is a general argument which tells us that the critical point is always stable, the attractor is always stable, but we need to analyze that in the non-supersymmetric case. So let's try to do that. Well, it turns out if we have n vector multiplets, that n plus 1 real directions in moduli space have a positive mass square, and n minus 1 directions have a vanishing mass. This is just from the vector multiplets. The hypermultiplets are not fixed at all, they are just flat directions. But since the hypermultiplets are sourced by the gauge fields, we need to then ask, by expanding the effective potential beyond quadratic order, about what the leading corrections are along these massless directions. This is a little algebraically complicated. Some tricks using group theory can prove quite useful. But anyway, the bottom line is interesting, and I'll just show it to you. The details are not important. The first correction is a quartic order, and there are 2 terms, and they come with opposite sign. This term comes with a negative sign, this term comes with a positive sign, and even in relatively simple examples, one finds, as you vary the charges carried by the black hole, that what is, for some range of charges, say, a stable non-supersymmetric attractor can become an unstable attractor, an unstable non-supersymmetric attractor. And so this illustrates the fact that there is a really rich structure in these attractor flows. You can have interesting phase transitions and so on. And it really is the beginning, in a sense, of the story. We need to understand this more fully and understand the full structure of these flows. Of course, in this whole talk, I should say I'm going to talk about only single-centered black holes. There's a corresponding story about multi-centered black holes in the non-supersymmetric case, which is yet to be developed. Okay, let's go to rotating black holes. Here, and ask about attractor behavior. Here the entropy function formalism proves quite useful. Of course, one of the main motivations in developing this formalism was to ask about higher derivative corrections, but you'll see that if you're dealing with complicated black holes as rotating black holes tend to be, even in a 2-derivative theory, this formalism proves quite useful. So the basic idea in this formalism is to not worry about the whole flow, but focus just at the end point, the critical point, that is the near horizon region. Now let's assume that an extremal black hole has a ADS2 near horizon region. If in addition we have spherical symmetry, I'll first just quickly discuss the spherical symmetric case in this formalism, just to make a connection with what we've already done, and then we'll go on to the rotating case. So if there was already spherical symmetry, we would get ADS2 cross S2. These symmetries impose restrictions on what form the metric and moduli can take. And then one finds that the most general values for these fields consistent with the symmetry can be obtained by extremizing a function, the entropy function, which depends on the moduli, the metric components, which I'm denoting by V, and the electric and magnetic charges of the black hole. So you have to extremize this entropy function. In other words, at the horizon, it is at a critical point with respect to these fields. And that then determines these fields in terms of the charges of the black hole, but the entropy function doesn't have the asymptotic values of moduli as parameters in it, and so that shows that the horizon values for the fields are again determined entirely in terms of the charges of the black hole. In other words, that there is attractor behavior. Okay, here are a few more details. To construct the entropy function, you take the four-dimensional Lagrangian and you integrate over the angular coordinates to construct, as it were, the Lagrangian in the remaining two-dimensional space, which is ADS2, and then you take a Legendre transform of that to get the entropy function. And I should have said that the entropy is the value of the entropy function at the critical point. Now, all of this is probably sounding very reminiscent to what I said about the effective potential, and in fact, in the two derivative case, there is a close connection between them. Here is the entropy function in terms of the metric degrees of freedom, V1 and V2, and the moduli, and you see that all the moduli dependence of the entropy function comes through the effective potential. A connection like this basically had to be true given everything I've told you. All right, so that's the rotating story. And now let's go, I'm sorry, that's the spherically symmetric story. Now let's go to rotating cases. Let's assume again that an extremal black hole has an ADS2 factor. When we did this analysis, we just made this assumption because it was true for all known cases. But since then there's a paper by Harvey, Rial and collaborators who actually show that extremality implies that the near horizon geometry has this ADS2 factor. Okay, so there is this factor, and in addition, if we have rotation, we don't get a SO3 worth of symmetries, but we get an U1 symmetry. Now, because of the smaller symmetry now, the functional form is less constrained. For example, moduli don't have to go to a constant at the horizon. They can vary on the horizon as a function of the polar angle. But that is a complication, but in the end it turns out to be not an essential complication. One finds one can still formulate an entropy function. Actually, it is now a functional of these functions, a functional of the modular fields and the metric components, which can also vary with angle, and it depends on the electric magnetic charges and the rotation angular momentum of the black hole. But again, by extremizing this entropy function, one can obtain the horizon values, or the full functional form now for these fields in terms of the charges carried by the black hole. And again, because the entropy function doesn't depend on any asymptotic data of the moduli, the resulting functional forms are only determined by the charges of the black hole and universal. Now, why does it work? The essential point is the ADS2 symmetry. You see, I told you that you construct the entropy function by basically reducing down to two dimensions after doing the angular integrations. And the two-dimensional theory in the rotating case, as in the non-rotating case, is the ADS2 theory. The only difference is that there are more fields which you get in this two-dimensional theory in the rotating case. With spherical symmetry, each scalar field in 4 dimensions gives rise to only one scalar field in 2 dimensions. Now, in the rotating case, for example, if you expand out phi of theta in some favorite basis of, say, Legendre polynomials, each coefficient is a field in this resulting two-dimensional theory. But that's not a conceptually new point. You just have to include all these additional fields. Not surprisingly, then you can write an entropy function, which in this case now determines all these fields in terms of the charges, and therefore determines the entire functional form in terms of the charges carried by the black hole. Once one realizes this point, it becomes clear that any other situation, for example one where the horizon topology is not spherical as in a black ring, but which also has a near horizon ADS2 geometry, will also give rise to the attractor behavior. And this point has been fleshed out since by Goldstein and Jena and some other papers. Okay, well, let me end by making a few comments about the connections with microscopic counting. In fact, if one thinks about these extremal black holes, non-supersymmetric black holes from a microscopic point of view, they are really quite intriguing. There is a huge ground state degeneracy which grows exponentially with the charge in this case. Of course, the degeneracy is not exact if we don't have supersymmetry, but you can use from the black hole description and using the fact that the thermodynamic description of these black holes breaks down only very close to extremality, one finds that the degeneracy will be lifted only a little bit, so that there are a very large number of states close to the ground state in these systems, and it is a puzzle because there's no supersymmetry, so why is there such a large degeneracy? But actually, furthermore, the attractor mechanism tells us that this degeneracy is actually robust. The attractor mechanism in effect gives us a non-renormalization argument, because as we change the coupling constants, which are the asymptotic values of the moduli, the entropy doesn't change, since the entropy is determined by the universal value of the geometry at the horizon. So that too is intriguing. Finally, in many cases, in the non-supersymmetric case, one can carry out a calculation in some weakly coupled microscopic description of the entropy, and one finds that it agrees with the Bekenstein-Hawking entropy. And that too then is an interesting question. Why is this agreement? And let me, in the remaining time I have, just try to address this point 3, in particular ask what light can the attractor mechanism shed on this agreement that is found in some cases between the microscopic calculation and the black hole Bekenstein-Hawking entropy. And this is a question we examined in this paper with Dabholkar and Sen. And the basic idea we tried to explore was the following. Going back to this comment I made about the non-renormalization, let's suppose that the non-renormalization which the attractor mechanism provides extends all the way from weak coupling, where say the microscopic calculation is well controlled, to strong coupling. Okay, if that were the case, then from the attractor mechanism we would be led to believe that the entropy should exist, that the entropy should agree. To put it another way, if the weak coupling region and the strong coupling region lay in the basin of attraction of the same attractor, then one would expect their entropies to in fact agree with each other. And this is the idea that we try to develop. But the way it exactly works out depends on what particular situation one is dealing with. So let me describe this in a little more detail. It's actually useful to just think about the supersymmetric case in light of the attractor mechanism. Let's say we have a supersymmetric situation which has a D-brane description. Typically the microscopic calculation is good when G string Q is very much less than 1. Supergravity is good when G string Q is much bigger than 1. Now, if it turns out that the dilaton is a flat direction of the entropy function, well, I told you the effective potential could have flat directions, but so can the entropy function. And of course, the entropy function can and does include all the higher derivative corrections. So suppose the entropy function with all these corrections has an exactly flat direction, then we can argue that going from weak to strong coupling will not change the entropy. This is because the entropy is the value of the entropy function at its extremum, and that by definition can't change as you go along a flat direction. It's not unreasonable in the supersymmetric case that there are such exactly flat directions. For example, in the type 2 example I told you about, the dilaton lies in a hypermultiplet and doesn't directly talk to the gauge fields which lie in vector multiplets. Now I should say that this argument I'm giving you applies to the entropy, not an index, because the extremum of the entropy function is the Bekenstein-Hawking world entropy. Of course, there are various assumptions. For example, there should be no phase transition. If the basin of attraction of weak coupling and strong coupling are different, then of course the entropy can and will in general change. There are also various other assumptions which we try to be careful about, which you can read about in our paper. But this is roughly how an exactly flat direction could explain the entropy in the supersymmetric case. Now, in the non-supersymmetric case, of course, we don't expect exactly flat directions. However, there can be approximate flat directions. For example, there can be a direction which is flat to all orders in the 2f coupling and leading order in 1 over n. Such an example arises in type 1 theory, where you break the supersymmetry of the black hole because of Orienti folding. The black hole we had would be supersymmetric in the parent type 2b theory, but after Orienti folding breaks supersymmetry in the type 1 theory, and since it's due to Orienti folding, this breaking of supersymmetry is a 1 over q effect. So one would expect to all orders in the 2f coupling that there is approximate supersymmetry, and therefore that there is an approximately flat direction. So here, of course, we deal with a case where we had approximate supersymmetry and use it. There are other situations for which I don't have time, where you can use a direction which is not flat but which is actually lifted. This is closer in spirit to the original idea I told you about, where if say this direction can be the size of a circle on which the different branes live. If the circle is big, then the states corresponding to the black hole lie in a field theory, come down in energy and lie in a field theory. And if the charges are such that you are in the Cont'd limit of the resulting conformal field theory, then you can calculate the entropy just from that information, as has been beautifully developed by Larson and Krauss. But then you can make the size of the circle small, and the states no longer lie in the field theory and can no longer then be described by the Cont'd limit of the conformal field theory in particular. However, the black hole geometry continues to show attractor behavior, and so you know that the entropy of the resulting state, even when the radius is small, must agree with what you found before. So this is a way in which directions which are not flat can also help you. Okay, well, let me say, we are not by any means close to understanding the entropy of all the cases, but at least some cases have been understood like this, and the entropy function is quite promising. So, and the attractor mechanism has proved quite promising. So let me conclude. Extremal non-supersymmetric black holes generically exhibit attractor behavior. The resulting attractor flows have a rich and complicated structure. There are interesting connections with microstate counting, and I feel kind of excited that there's probably much more progress to come. Thank you.
Thank you very much. Are there questions or comments?
So at the beginning, when you were talking about this effective potential, you said there were two conditions, and one of them was that the second derivative of the potential had to be positive. So there's a similar condition in the entropy function approach, that the second derivative should be positive in some sense?
Okay. You know, in the entropy function approach, we give up on something. We can include the higher derivatives, but we don't analyze the whole flow, only the critical points. And so if there is a particular critical point of the entropy function, we do not know just from the entropy function analysis whether it's stable or unstable. And so in the two derivative case, that analysis can be done along the lines I said, but with higher derivatives, it's a much more complicated story, because you have higher, if you say have a fourth order equation, there are additional solutions to the equations, and some of them are spurious and so on. So it's not a very well understood situation, in other words.
But it's not meaningful to talk about an unstable attractor flow, right? Because if it's unstable, it's not an attractor.
That's true. That's true. In situations where, let's say, you found a single solution as a critical point to the entropy function, you might think that that would be an attractive one, but you would only be sure if you could analyze really the full flows. That's right. But this at least tells you what the possible endpoints can be, and some of them could be stable endpoints. That remains to be seen.
Any more questions? There's one in the back. Andy?
So did the argument about the entropy being, if you're stayed in the same basin of attraction for small GSQ and large GSQ, does that depend on the existence of a well-defined horizon, or is it just a property of the low energy effect of supergravity? What's bothering me is that if GSQ is small, we might not be able to talk about a black hole at all.
Yeah, that's true.
So you can still talk about the effective potential.
That's true. I should have said that. That's exactly correct. So let's suppose supergravity was good here and not good here, where the microscopic description is weakly coupled. Then you'd certainly expect that supergravity should break down here. But if you ultimately exit out to the same attractor, and that attractor then that attractor might admit a good description in which supergravity is weakly coupled. This doesn't have to happen, but it could happen. In other words, suppose there was a black hole which you could analyze starting with the coupling constants here, and it was weakly coupled in supergravity everywhere, including at the horizon. Yeah. And then suppose it was the case that this was also the attractor when you started at weak coupling, then what would have to happen is in between. So when you started weak coupling, supergravity is no good, but by the time you make it to the horizon, since you're opening out into the same geometry, supergravity would become good. So that's the way the story would have to go here. In cases where you have a flat direction, what really happens is that in the weakly coupled description, supergravity is never good. But since it's a flat direction, you can argue that the entropy should not have changed, and you can compute it at, say, strong coupling, and it must be the same as what you get at weak coupling.
Can I ask another?
Yes.
So since you have an ADS region near the horizon, could it be that these these Hessians are, actually could be negative, but above some kind of Brighton-Lohner-Friedman bound? Do you actually need them to be... Wouldn't that be enough?
I don't think so. As far as I know, I think ADS2 is a little different, but I can't say I've analyzed it fully. As far as I can know, I can tell the moment you have a single negative eigenvalue, it's enough to make it's enough to repel the attractor flows away. And I think it's different. ADS2 is a little different from ADS3 as far as I know in this regard. Even in the ADS3 case, okay, as far as I can tell, this is the situation.
You could ask the same question about black string attractors in 5 dimensions where you have ADS3, right? Non-supersymmetric ones.
Right. I think your entropy function should have a kinetic term in this case, and then it's the same phenomenon as Friedman-Brighton-Lohner. So my answer to your question would be yes.
What was the question to which the answer was yes?
That there could be a Friedman-Brighton-Lohner thing because there is kinetic energy in the entropy function. If you have the rotating black hole.
But I think ADS2 is a little different. As far as I can tell, this condition, if it's not met, will not give rise to a stable attractor. You really will fly away along the negative eigenmode directions. But okay, we can talk about it more. And
one more question there.
So I have a couple of short questions about the applicability of your discussion to black rings. So the first one is that the near horizon geometry, I suppose it's ADS3, not ADS2. And the second one is that by attractor, I suppose you mean that the moduli at the horizon will depend not only on concept charges, but also other quantities like dipoles, etc.
Yeah, that's right.
Which are not determined asymptotically.
Yes, I should have said that. There are additional charges, quote unquote, which arise, which if you're just doing the analysis sitting at the horizon, you can formulate sort of additional charges, but they're not really charges that's seen at infinity, and those would also then enter the entropy function. That's right. But after incorporating, so the spirit of the analysis here is to just look at the near horizon geometry, write down, which has whatever symmetry it has in this case, write down the most general ansatz for the metric and other fields consistent with those symmetries, and the most general value for the gauge fields. And that would then also include these dipole charges, then construct the entropy function with these parameter charges put in, and that would determine everything in terms of those charges, including the dipole. But you're right, those would enter here. That's true.
Okay, thank you. I think we should stop here in view of the time. Let's thank the speakers once more and go to coffee.